Okay, we'll start with Jablonski diagram. So Jablonski diagram, as you can see, this is a particular diagram. So when the photon molecules are getting excited, they move from the S0 state to S1 state to S0, S1 and S2. So as you can see, this is the graphical representation or a diagrammatic representation where it is between energy and fluorescence and phosphorescence. Okay. So when the molecules are absorbing the photon or the light particles, they are able to get excited and they are able to move from S0, S1 and S2 state respectively. So this is Jablonski diagram. Okay. So first let us see the content of it, then we'll move to the diagram for better understanding. So now as you can see, this is a schematic energy level map which explains what happens to a molecule after it absorbs a photon. So these are the key points. S naught is a ground singlet state. So here in the ground singlet state, all of the electrons spin are paired electrons. So paired electrons, I'm so sorry. Sorry about that. So the paired electron, the ground state will be always paired only. So one will be in one direction, another will be another direction. So they both will be in opposite direction, but they're always in paired in the ground singlet state. That is S naught. Okay, then see, ground state is the lowest energy state. Then the observe photon and they move from S naught to S1 and then to S2. So S1 is the first excited singlet state and S2 is the second excited singlet state. Here also the electron promoter, their spin are still paired only. Clear? And then comes the T1, that is the first excited triplet state. So here the electrons are now flipped. So it will be like one electron in this direction and another electron, another here thing also will be in like one. I'm so sorry, I don't know why it comes like this. One will also be like this and another will also be like this. So both will be in the same direction because one electron got flipped. So now this T1, the first excited triplet state, has lower energy than compared to the S1, that is first excited singlet state. So S0 to S1 to S2 and then it goes to T1. So T1 is where the electrons are paired but one is getting flipped. Okay, now the spins are now in parallel direction. So each electronic state has multiple vibrational sublevels are there. So these molecules can exist any of these vibrational levels. So, okay, either they can be of S0 or S1, S2 or T1. They can be of any of the vibrational level depending upon the amount of or intensity of the photons that has been observed by them. So as you can see the diagram, they go from S0 to S1 to S2 and then it goes to triplet state. As you can see, there is an internal conversion which takes place. So from ground state, the molecules are observing all the photon or light energy and they're going from the ground state to the excited state, that is S1, S2 and T1 respectively. So here there is internal conversion also that is taking place. The S2 can come to S1 or S1 can become T1. So a lot of internal conversions can also take place. And one more important thing is that there are two type of processes that is taking place in Jablonski diagram, that is radiative processes and non-radiative processes. Radiative processes, there are two things that is happening, that is fluorescence and phosphorescence are taking place. We will deal with it in detail what is fluorescence and phosphorescence. Just now you can see that there are two processes that is coming under radiative processes, that is all the light or photon is being observed by the molecules and they exhibit two reactions, that is fluorescence and phosphorescence respectively. Non-radiative processes which the molecules are now undergoing vibrational relaxation, that is basically from the excited state they are jumping back and coming to the ground state and they are losing all the energy, they are basically coming to a relaxed state. So that is called as vibrational relaxation. This is a non-radiative process. So radiative process, you have fluorescence and phosphorescence. Non-radiative process, you have the vibrational relaxation. I hope Jablonski diagram is clear. As you can see, S0 is a ground singlet state. S1 is the first excited singlet state. S2 is the second excited singlet state. And T1 is the first excited triplet state respectively. So now what are the important transitions that is happening? Absorption from S0 to S1 is a very fast process and the time taken is only 10 to 15 seconds. Vibrational relaxation is when excess of the vibration energy is lost in the form of heat and the molecules are now coming from the excited state back to the ground state, and the time taken for this is 10 to 12 seconds. Okay. And now coming to internal conversion, that is IC. Okay. So here the radiation less transition is happening. That is S2 is coming back to S1. So here energy is released in the form of heat as well. Then we have inter-system crossing that is happening. Inter-system means basically from between states that is happening. So from S1 to S2 or S2 to T1. So different interconversion between the states is happening from ground state to excited state, but there is different spin. So S1, if you see, there are opposite spin, but T1, they are of the same spin. One electron is getting flipped and both of them are now, so S1, if you see, they are paired in opposite direction. T1 has now become unpaired, but they are in same direction only because now the electron has got flipped. So that is called as inter-system crossing. So basically there is interconversion as well, and the paired electrons has now become unpaired electrons and the spin has also changed its direction. So that is called as inter-system crossing or ISC. So I hope all the important transitions are now clear. Coming to fluorescence. Fluorescence is nothing but the light, so the molecules, when they are observing all the light, they are emitting some light. So emission of the light from an excited state to the ground state, back to the ground state, that is called as fluorescence. So as you can see in Jablonowski diagram also, so S1 is the first singlet excited state. From S1 to the S0 is the ground singlet state. So it is coming back. So the emission of light from the excited singlet state to the ground state, this is happening from S1 to S0. That particular process is called as fluorescence. So when you see the characteristics of fluorescence, means it is a very fast process. It happens very quickly within a few seconds, and this fluorescence process stops immediately after you remove the light source. So the total lifetime is 10 to 9 to 10 to 7 seconds. So this is a particular time. So 7 to 10 seconds, a maximum period. The amount of light is basically emitted from the particle or the molecule to get from an excited state to ground state they are able to go, means that is basically the fluorescence process. So I hope fluorescence is now clear. The example is fluorescent fluorescence. So now you can see it's a higher energy emission. It takes place very rapidly within a few seconds, and it is short-lived because as soon as you remove the light source, the fluorescence process completely stops. So it's a short-lived process, and usually the type of light that is used in fluorescence process is visible light only. Okay, so let us see some key features of the fluorescence process in detail. First thing is that it occurs from the lowest vibrational level of S1. So that is called as Kasha's rule. It always starts from the lowest vibrational level, from S0 to S1 to S2. So it always, the fluorescence process means it starts from the lowest vibrational level because S0 is ground state. So here no vibration, no molecules are getting excited. So it's basically in a relaxed state. So molecules, when they are observing the light, they move from the ground state to the first singlet excited state. So S1 is the actual state where the molecules are observing the light and they're undergoing vibrational reaction and they are getting excited. So they are occurring in the lowest vibrational level of S1, that is the Kasha's rule. And the lifetime that is taken for this is 10 to the power of minus 9 to 10 to the power of minus 7 seconds respectively. So 10 to the power of minus 9 is nothing but nanoseconds. It means it occurs very fast, very rapidly it takes place. Okay. And if you see the emitted photons, so when fluorescent molecules, when they are emitting the photons, they are of very low energy. That means they are having very low wavelength. Okay. So compared to the observed photons, see, for example, they are observing lot of photons, means, but the amount of photon that is being emitted out in the fluorescence reaction is of very low energy and is of very low wavelength. So this particular shift is called as Stokes shift. Okay, so that means the emitted photon is much comparatively less energy and wavelength than that of the absorbed photon. This particular shift is called as the Stokes shift. Okay, and this particular reaction is short-lived because it stops immediately after the light source is removed. And now the spin multiplicity is also conserved. As you can see, singlet to singlet. Only it happens. So the spin is, it is spin allowed and is fast as well. Okay. So now I hope fluorescence is clear. Let us go to phosphorescence. Phosphorescence is also similar to that of the fluorescence only. Only thing is that the emission of the light will take place from the triplet state, that is T1, and it goes to the ground state, singlet ground state, that is S0 it goes. So here phosphorescence is a very slow process. So fluorescence was a very fast process. Phosphorescence a very slow process, and this particular process continues even after the light source is getting removed. And if you see the lifetime, it is for only 10 to 3 seconds or to several hours also it can go. Okay. And here, example is that it glows in the dark materials as well. Phosphorescence can also it can glow in the dark materials as well. So they are of lower energy emission. They are long lasting. They continue even after the energy light source has been removed. So this is about the phosphorescence reaction, and it happens from T1 to S0 transition. So here you can see here ISC to first populate T1. So here from T1 S0 it is happening, from triplet to singlet is a very slow process that is happening, and the lifetime is for 10 to the power of minus 3 seconds to several milliseconds also it can happen. And there is afterglow reaction, that is after removing the light source also still it continues to glow. That is why it is a very slow reaction as well. And the amount of photon emitted, only difference is that there the amount of photon emitted is of lower energy and lower wavelength than that of the observed photon in case of fluorescence. But in case of phosphorescence, it has lower energy, but it has a longer wavelength than the fluorescence. So that is about the phosphorescence. So I hope fluorescence and phosphorescence is now clear. But where do we actually use fluorescence and phosphorescence in the field of forensic science? What is the forensic relevance behind this means? As you can see here, fluorescence is used to detect latent fingerprints. What do you mean by latent fingerprint? Invisible fingerprints. So in a crime scene, the victim or suspect, they might leave their fingerprints by mistake. Okay. So those latent fingerprints, which is not visible to our naked eyes, by using dusting powders, fluorescent dyes or powders, we can use it to analyze the invisible or latent fingerprints in the scene of crime. Even to identify drugs and explosive question documents, we can use UV light as well. So here and all fluorescence is used. In case of phosphorescent materials are used in security printing, like this your to check the if it is a counterfeiting of currencies and all, there are fake currencies and all is there, no? So you can use phosphorescence to see the basically the Gandhiji's photo, ink stain, lot of things you can analyze it in detail. Okay. So that is about the forensic relevance of phosphorescence. As you can see, the difference between fluorescence and phosphorescence, it occurs from S1 to S0, it occurs from T1 to T0. It is a fast reaction, it slows reaction. It stops immediately after the light source is removed. It continues even after the excitation, and it is for a few nanoseconds for lifetime, but this is for milliseconds to even hours, and also it can go. Here in fluorescence, the spin is allowed. In phosphorescence, the spin is forbidden. Okay. Now coming to non-radioactive processes. So radiative processes only we have fluorescence and phosphorescence. In non in non-radiative processes, we have nothing but the relaxed state. They are in the ground state basically. The molecules are not getting excited. So here the excited molecules, they will lose their energy without emitting any light, means that is non-radiative process. So we have vibrational relaxation, internal conversional, intersystem crossing and all. So vibrational relaxation means basically all the energy is lost and the molecules are now coming from the excited state to the ground state, and the energy is lost in the form of heat, means that is vibrational relaxation. Internal conversion means, so from S2 to S1, so from one state to another state, the conversion is taking place, but there is no emission of photons that is involved, means that is internal conversion. Intersystem conversion means we know that, right? So here also from singlet state to triplet state, there is a conversion that is taking place. Here also there is no photon emission is involved. So these particular processes all they compete with fluorescence and phosphorescence respectively. So that is about non-radiative processes. Okay. Now coming to another important topic, that is quantum yield. So here the definition is that ratio of the number of molecules that is reacting or the number of photons that is emitted. So number of photon molecules that is getting observed, that is reacting, and the number of molecules or number of photons that is observed. So the ratio between these two are called as quantum yield. See the number of photons that is observed to the number of molecules that is transformed, or how much they are doing a photochemical reaction. That is called as quantum yield. What is the yield of that particular reaction because of the absorption of the photon? That is quantum yield. So in case of fluorescence and all, if you see, means the rate of fluorescence is divided by the rate of absorption. So if you see quantum yield, it ranges from 0 to 1. So 5 is equal to 1. So it means that every observed photon, it results in the in that process only. If the 5 is lesser than 1, means it's a competing process for interconversion or for interstate conversion and all. It will reduce the efficiency of that particular process. That is about quantum yield. So now there are different type of quantum yield. You have reaction quantum yield and your fluorescence quantum yield. Reaction quantum yield means it measures a chemical transformation. How does a chemical reaction that is happening? So what is a chemical transformation that is involved means that is reaction quantum yield. Fluorescence quantum yield means how much amount, or it measures the fluorescence efficiency in a chemical reaction, means that is fluorescence quantum yield. So now if you see the interpretation, we know that, right? Quantum means one molecule reacts with one photon only. So the energy that is lost through the competing process, it is always lesser than one. If the quantum yield is greater than one, means it is a chain reaction. That means one molecule can react, one photon molecule can also yield many molecules as well. Okay, so it is not like one photon per one molecule. Sometimes one photon can react with multiple molecules yielding in a chain reaction as well. For example, you saw this as well. H2 plus Cl2 gives us 2 HCl. So the quantum yield might exceed around 106 as well. This is about quantum yield and the types of quantum yield. If you see an example, rhodamine B is again a powder. Okay, it's a dye, basically fluorescent dye. It has a quantum yield of equivalent to 0.97. So that means it has a perfect fluorescence. So that is why it is acting as an ideal standard. So in forensic labs and all, they use it as a standard material as well. Okay, standard dye. So it is a heavily quenched molecule. That means their quantum yield is near to zero. That is why it is a heavily quenched molecule. So what is a forensic relevance of this? High quantum yield means it yields fluorescent reagents like ninhydrin. Ninhydrin is again another chemical reagent which is actively involved in reacting with the amino acids of sweat and all in your fingerprint and all. A fingerprint has some sweat, right? So it reacts with the amino acids of the sweat and also helps in detection of certain fingerprints and all. So ninhydrin acts like a chemical reagent for analysis of latent fingerprints and all. So for these, ninhydrin, then you do these are fluorescent reagents. So they fluorescence under UV light and all. Even luminol, DFO are all chosen fingerprint detection because they produce maximum signal. So one photon will produce maximum number of molecules to the fluorescent under the light properly. So giving a proper analysis of the fingerprint in the crime scene. Okay. So now coming to photosensitized reaction. So it is a reaction which a molecule, they do not observe light directly. It is actually activated by another light observing substance that is called as sensitizer. So they do not observe all the light directly. So there is another light observing substance. That light observing substance is getting activated. It's very sensitive. So they react to even a small reaction as well. They easily get activated, and that is called as a sensitizer. So there is a mechanism involved in photosensitized reaction. First step is that sensitizer will observe all the light. So sensitizer, when it reacts with light, it goes to excited state, that is S star. Now the energy is getting transferred, this excited state along with the energy that is activated. Now it goes into the singlet state. Now the sensitizer is getting the energy, right? So it forms A star. Now the activated molecule, it basically forms product. As you can see, there is an energy transfer that is involved here. So the sensitizer now reacts with light and goes towards excited state. Now this excited state, when it reacts with the activated molecule, it basically forms an activated molecule. Now this activated molecule, now it reacts means it can produce different products as well. Okay. See, for example, photosynthesis. So here chlorophyll is acting like a photosynthesizer, basically like a catalyst which basically speeds up the chemical reaction in the formation of glucose and oxygen and all. Similarly, common sensitizer are benzophenone, rose bengal, and chlorophyll can also be used. So these photosensitizer will basically speed up the reaction to happen in a faster rate. So what is the forensic relevance behind it? Photosensitized degradation or basically destroyal of the photosensitized material is relevant in analyzing photodegradation of drugs, dyes, textile fibers, or even the ink in the documents and all, forensic documents and all. When they are exposed to light beams, sometimes they might get degraded in the light. So the light degraded samples now can be analyzed by using these photosensitized material because it's sensitive to light. So they will produce the results properly. Clear? Now the last is energy transfer process. So here energy transfer process is when energy transfer happens. So we know, right, from excited molecules, another molecule. So from ground to excited, from one excited to another excited. So there is a transfer of energy that is happening. That is energy transfer process. So the two main reactions in which the excited energy moves between the molecule. As you can see, there is radiative energy transfer. The excited donor will emit a photon. Okay, this emitted photon is then observed by the acceptor. Okay, so that is energy transfer process. In case of radiative, non-radiative means we have two important process called as Foster resonance energy transfer, that is FRET, and Dexter exchange transfer. Two transfer reactions are there. They are non-radiative energy transfer reaction. So FRET is basically a long range. It is dipole-dipole coupling basically takes place. So here the efficiency drops. So in case of biophysics and forensic DNA analysis and all, we use this FRET. So they are basically, there is no emission of photon that is involved. So non-radiative energy transfer means there is molecules are in a relaxed state. They are basically in the ground state. There is no vibrational reaction that is happening. The molecules are not getting excited. So there is no emission of photon involved. So now the electrons are doing dipole-dipole coupling. There is pairing of electrons that is happening here. Okay, so they are mainly used in biophysics and in forensic DNA analysis and all. Now coming to Dexter exchange means here the orbital there is overlapping. So the electrons configuration will be there, right? So in orbitals there is overlapping of orbitals that is happening. So because of the overlapping of orbitals they are extremely sensitive. That is why they are used in triplet state sensitization reaction and all. Since they are very sensitive and all, we can use it in triplet state sensitization reaction. That is about FRET and Dexter exchange transfer. So as you can see, FRET, it's a long range transfer. Dipole-dipole interaction takes place and the distance, it's distance dependent, depends upon the distance. So it is used in biophysics, biochemistry, and in molecular biology. And this is very important. The efficiency is directly proportional to R61. That is very important. So this is about FRET. So Dexter energy transfer means there is electron exchange mechanism that is happening. So since the overlapping of orbitals are happening here, the electron exchange is happening here. Electron exchange is happening means there is a short energy transfer only takes place. So energy transfer that is involved that leads to the overlapping of the orbital means that is a Dexter energy transfer. Okay. Now coming to the practice MCQs. Which of the following law that states that only radiations which are observed by a reacting system can bring about a photochemical change that is happening here is what is